Okay, good afternoon, everybody. So, another reminder. This is, I believe, our final makeup. It's the same. The same one should be online at that point. But what it means is next Wednesday, Ariel. Thank you so much. Not here today. Oh, sorry. Didn't see you, man. But you're going to start on the Wednesday, and then we're going to carry through with Boris and Haley. Basically, what we'll do on the Wednesday too, just because it's our first one in, is it's only going to be your presentation. It'll give us the most time to kind of walk through it and stuff, so no problem there. In advance of that one too, like if the timing's in place, please do send me your PDFs. I've populated up the Canvas site right now, so everybody's name should be on the blocks as it is. I'll link over your PDFs to those specific ones. When you have your talks and everything ready to go, please hand them over to me, and then I'll get them uploaded onto the site as well too. Part of the whole thing as you're setting up to, we'll do the same thing that we've done before, which means you're going to be recording your presentations, and we'll upload them just like that point too. So there's a little bit of tech, blah, 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 to kind of get ready stuff. We'll practice it in. I've also emailed everybody with your evaluator. So you should have all received an email from me assigning you to you will be evaluating a person. Has everybody gotten that from me at some point? If those days don't work out for you, please let me know, and then I can reassign again based on if you're going to be out or something like that for other days. I will give you guys a Google Sheet. What this one is it's just like a questionnaire or survey. Use that to fill out your evaluation, because then they can just aggregate them together anonymously, and then we can pass them back to the students as it is. Anything else leading up to logistics for next week? Cool. All right, so what we left off on is introducing this concept of coupling together multiple pathways where we're doing selectivity now, and we're looking at energy level diagrams for both your delta G and your delta G naught, delta G double dagger, are going to be involved in some kind of a selectivity pathway. So a case like this, we're really saying that in our starting material, it exists in this case in this kind of middle envelope. So we're looking at these energy diagrams usually as kind of an opened book, where your starting materials or starting reaction conditions kind of exist in the middle, and then usually what you're representing is two possible products to the left and to the right. And the way to read this one is, in this case, this is a dynamic resolution we introduced last time, where you have two different enantiomers, these two guys here and here, where they can equilibrate back and forth by just an acid-base reaction. So that proton on this alpha position is acidic enough where deprotonation there can give you a scrambling of that center. So you're going by way of the enolate. So just as far as again, if you're drawing this one out by sketch, we know that the energy here and here must be identical because these two molecules are enantiomers of each other. We're assuming that the energy of the enolate is going to be higher in energy. It's an anionic complex. And then we're assuming that the energy barriers to access that one is going to be facile. We're saying that if we're drawing it out this way, these two molecules can equilibrate rapidly between each other, where what we have then is a selectivity step. Once we pass that selectivity step, there's no coming back. What we're seeing is jumping over that final barrier gives you either one product or the other. So visually from this one, we have two different energy. The equilibrium here, you can think of it as one population where whatever concentration of my two starting materials is just going to be this kind of aggregate of all, both isomers, but also your enolate. In that case, the selectivity is probably going to favor this one, and that's just graphically, we're showing that by saying the transition state to reach this one here, or going from that component up here, is what's giving you that preference. But the absolute selectivity could actually be measured as the relative energy difference between the two possible transition states. You can imagine that even though I've got a couple different populations, as long as I can rapidly move back and forth between these two, it's almost like you can collapse that whole energy surface together. And really, what I'm saying is it's that gap right here, what we call the delta G double dagger, the difference in energy between the two transition states, is what's giving us some kind of a selectivity. That's also where we can calculate what the relative energy difference or the rate difference is. Just digging into the actual case, this is a dynamic kinetic resolution. This is one of the classic ones that started off where you actually couple this equilibration to a Newari hydrogenation. What you're doing here is you've got this precursor starting material, and again, the reason this was invented is kinetic resolutions on their own. The purpose there is what you're doing is you're taking two possible stereoisomers, diastereomers or enantiomers. You have a chiral, usually catalyst, something that's going to select between the two. So really what I have is a catalyst that can look at these two, pick one of them. In this case, this one here is the preferential reactive molecule, which means this one's going to react fast with whatever your step is. This one reacts slow. Now, if this was a normal resolution and those two starting materials could not equilibrate, all we're really doing is taking a one-to-one population of two enantiomers, and I'm reacting away one, leaving behind the other. So in a perfect situation, if those two were not connected, what you could get is a 50% conversion where one enantiomer is left behind as the starting material and one enantiomer is converted to the product. Good case there is you would have a clean population of the selective reduced product, but then also unreacted starting material, which you would then separate and say, great, I've got two chiral materials. Dynamic kinetic resolution was just valuable because it means that we can actually take that 50-50 population of enantiomers. Since they're effectively the same molecule because they can equilibrate within each other, you can convert all of this population here to a single target molecule just because they can re-equilibrate. It's another way to just sort of to use this chirality step. So the principle behind it, or why it works in this case, is the ruthenium binap complex is doing a selection onto the starting ketone. So what you have here is two enantiomers, identical energies to each other. The transition state is just a geometry where your ruthenium binap complex is doing a reduction or selecting for one enantiomer versus the other. Since it's a complex where this chiral molecule and this chiral molecule impact each other, depending on the geometry of your starting material, your transition state is no longer enantiomeric. They are now diastereomeric because even though part of the molecule, the ketone, their enantiomer is an identical energy, your catalyst is now chiral, so the interaction between the two is a diastereomeric complex. You have basically, think of it as R catalyst and R starting material, R catalyst and S starting material. So that gives you an energy difference between the two. What it does effectively is light up that part where you've caused an energy difference between what is effectively the irreversible step here, in this case the hydrogenation. And again, this is where we can go through and design this. In this case, the way that this was built out for the Nuardi catalyst was based on this kind of wall flap model. It's a steric control point where what you're saying is that the geometry has to either match or mismatch depending on what that sterics is. We don't have to go into any more detail. But the point of it is it only happens because what we've done is discriminate to create a diastereomeric pair of different materials. So even though there's an equilibration, the energy level diagram we have on the left in this kind of reactant population, this here is just being treated as one bucket of material. So even though there's an equilibration between the two different ketone starting materials, as long as it's rapid, the way that we end up sort of breaking this down is just to say that since it's a rapid equilibration, we just put it into the same bucket as one composition. Again, it's possible if it's much more rapid than the other cases. Now this gets to a point that I want to sort of dive into. You know, now that we've talked about how temperature affects K, we've talked about various ways of saying, okay, I can look at one K versus another K. We're now walking back and forth between energy level diagrams, so the relative delta G double dagger of a system, but also the rate constant K. We've also got equilibrium effects. We could tell which of two possible, let's say, diastereomers was more favorable if they were intermediates. We can actually go and use primary thermodynamics as well as the rate equations we have to kind of get them into a general idea of saying how big does that energy gap here, have to be in order to give you some kind of a selectivity. So, a priori, you can kind of look at this and say, what is the sort of energy gap I need to sort of hit? And why that matters is, especially if you had some idea of what those delta G values are, you could potentially come back and say, what temperature do I need to actually enforce in order to really exacerbate or stretch that gap to get you a higher selectivity? So one thing I want to go switch over quickly to is laptop. And again, I'll share with you guys this Excel sheet. I just want to quickly go over sort of a step-by-step part that you can do to help you basically make a good guess for what this kind of relationship is between your rate constant, your K values, but also the energy values. So all I've done here is I've populated out an Excel sheet. This is just the diagram that we're sort of talking about right now. And we're just trying to say, like, look, if this gap was some size, what's the rate constant associated with that energy barrier? Now, on a diagram like this, we could actually go through and use both, your normal equilibrium relationship to say if I made a guess of how big this delta G value was, I could come up with some size of what capital K value, my equilibrium position is. Imagine if this was a fully equilibrating system between these two. It'd actually be sort of ranking the delta G between energy state and energy state here. Or if this was an equilibrium, you could do the same component. So you could start off empirically by adding sort of just general numbers and then walk back and forth between size of K value to give you sort of an idea of how big or small these distributions might look. Same thing for this. This is your iron equation. So you can go through and say, I know the Boltzmann distribution constant, I know H, I know R and T. I can go and say at some temperature T and some activation energy, delta G double dagger, what K would I actually come out from that one? So this is also back to, I mentioned, when we started talking about things like the Meyer equations. If you don't have sort of a general understanding of what K values are normal rational, this is something that can be useful to you to kind of ground yourself. So as a quick part, all I've done here is I've got this cell, which is just the temperature in Kelvin. So let me actually add that. So that's my temperature in Kelvin. Over here, this is my free energy. In this case, it's the delta G double dagger, the free energy of activation in joules. And I've set it to 80,000. And from that, the rate constant here, all I've done, and this is where you can go through and look at the equation, but all I did was take the Arrhenius equation here, and I'm asking it to calculate K with the Boltzmann distribution, the temperature, H, E, or the exponent value raised to the minus delta G RT, where my constants are just over here. There's the Boltzmann constant, Planck's constant, and ideal gas constant. So I'm taking those three values as my constant. I'm taking my temperature and the energy I input, so these are my two input values, and it's going to return the rate constant from that product. So just as a quick gut check, at 298, a delta G double dagger of about 80,000 kilojoules, or 80 kilojoules or 80,000 joules, your rate constant is in the order of about something 10 to the minus 2. That's kind of normie, right? That's about normal. And the thing is, if you ever want to look at that as well, what does that value actually mean? If you think of it in terms of absolute reactions, one thing you can do is say, if this is my rate constant, let's assume that's the rate constant for an SN2 reaction. Okay, I could take that rate constant for an SN2 reaction, single step, and I could calculate the half-life given that point. And you can sort of do a gut check and say, if I ran a simple reaction, SN2, that happened to use that rate constant, at a normal concentration, let's say 0.2, 0.3 molar, how long would this reaction actually take me? Is it months? Is it weeks? Is it seconds? Is it femtoseconds? And you can sort of go through that last part of just saying, what does this value mean in terms of practical realities of what your experiments you might do? But what you'll find is generally observed rate constants usually sort of fall in this range of times 10 to the minus 6 or 7 up to times 10 to the plus 6 or 7, right? That's kind of the realm of sort of normal things up to diffusion limit or whatever. Now again, what it means then is you can come back over here and say, I could go through this and say, all right, well, what's the energy relationship? What does it actually mean if I was going to be guessing values to maybe populate onto this point? Because remember, that's just one case against here. Really what I'm saying from a selectivity perspective, how much of this one versus how much of this one is going to come down to how big this barrier is, so it's delta G double dagger, versus this delta G double dagger to get you some difference between the two. You're basically saying rate versus rate between those. So what's a normal energy difference you can expect for these two and how it might outcome over here? You can just go through there and say, I'm going to only look at one half of this equation and say, if I was to index the free energy value, I'm going to try a whole bunch of different free energies and see how does that outcome look. Now you could just sit here and say, well, all right, what if it was 90,000, okay? Automatically, in this is 900,000. And you can see that, that sort of thing, we've gone to the point of this is, the life of the universe kind of thing, right? This is the half-life that you could go through. This one seems irrational there. But what I like about having something like this built into an Excel sheet is you can do this kind of hunt and peck and say, as I make something bigger or smaller, I can gut check this on a single value. A much better thing to do, though, is you can use this iteratively to show what if I was going to scan over a larger range. So what might you do if I'm trying to set up, let's say, a plot or like a matrix of a whole bunch of different free energy values, then the corresponding rate equations, where I want to visualize this to say, what's my kind of top and bottom? I gave you this value of like, okay, 80,000 is a good center point. But if we're looking for something between ranging minus 10 to the 6 to the plus 10 to the 6, what's the energy that kind of comes out from that one? How might you find that? Give me an example of what I should punch into the Excel sheet to start to do this kind of scanning exercise. Besides, you know, this, don't sit there and just do, okay, it's like playing Go Fish. Is 100,000 good? Oh, that's about the top end, whatever. Like, instead of doing iterative one-by-one values, what might you do to set up this sheet to help you out? Yeah?
Could you set up solver to estimate how long it takes based on K and then set bounds for that?
You could. That still is individual value. That's where you're scanning for like maybe some point. But that's advanced. You might be able to. There's a really more pedantic way. Yeah? You could, and then what you could do is say, we could flip it around. You could say, I want to solve for K given, or no, I'm solving for energy given K, and I just want a maximum and minimum. That gives you two values, absolutely. You're no fun. The way that I work on this part, just so I don't have to do any algebra or anything else, if I have a value, all I've done here is that's my energy, this is that same equation, my same rate equation I have over here, but I've tied those two values together, right? Now what I'm going to do is say, all right, obviously 200,000 is way too slow, right? The energy value, or the rate constant I get from 200,000 is down in times 10 to the minus 23. No good. Now I want to scan through this, and I want to do this visually. So what I'm going to say is, I want this, this cell to equal the one above minus, let's say, 1,000. So what I'm doing is, I know that that's too big. I want to knock it down by some value. And then what I'm going to do is go over here, grab this, and paste it out. And what I'm doing with that equation is I'm doing the same calculation where I'm indexing what I'm calculating this. So it's going to move as I slide down. So now what I can do is just say, all right, I can take this value, and I can populate it all out. Bloop. And then I take this. Here, wait. Does anybody know about this trick in Excel? Bloop. Bloop. Right? Double-click corner, copy down. There's a whole book called Excel for Chemists. It's phenomenal, right? Hotkeys and other things that you can go and do. All right, so all I did here is now I've created that range, and you can see that, all right, based on doing that, sure, I'm doing better, but I'm still only running to about times 10 to the 19. So it's not enough, right? This is still that point. So basically, this is too granulated. What I could do if I want to visualize it is I like taking, if I've got this XY, now I can go through, I go insert, oops, where's my insert? Bloop. And I quickly go to a graph, and I have an XY graph, and I can sort of, I like having the composition of both my numbers and then also the graphical representation I've got against it, because it gives you sort of a quick tangible way to say what's going on here. And here I'm graphing energy versus rate constant. If you ever wanted to kind of switch the two, at least on Excel, not on Excel, excuse me, on Mac, I can go in here and say, no, I want that to be X, and I want that to be Y, and then boom, I've got the inverted graph I can go play with as I go through here. So that gives you a little piece to it. Now again, when you're on a scale that's this big, where you're getting this kind of behavior, that's often why you would probably go to something like, I want the log of this specific one. Because once you do that, now it's a little bit easier to visualize that sort of outcome. So I want, instead of what's on there, I want this one. Bloop. You can compress or extract the two. Oh, sorry, other way. I want the log, other point. I want this one to move over there. So now we've got something that's a little bit more linear, because we're talking about orders of magnitude. It's a little easier to see on a log plot of kind of what's happening. And again, that makes sense. We know what the Arrhenius equation is. We know it's a linear part. What I'm saying is, you can go through this now and say, all right, that's not very useful. We're still times 10 to the minus 19. If you want it to be really dynamic, you could actually build a sheet where a single value, let's say the difference, so diff energy was here. That way what I can do is say this cell is no longer times a fixed value. It's actually minus this point. I'm just going to float it out right now. I'm going to fix my spelling mistake. And I'm going to say the difference in energy is going to be equal to, let's say, 5,000. And I'm going to populate, wait, we got to do a dynamic reference, bloop, boop, number signs, and then we bloop that way. So now that it's set up this way, I've got one value. I can sit there and say, well, what if I scanned over 10,000, bloop, right? And now you've got a really quick way of sort of expanding and contracting across this. It's a very simple thing where I can play with just this number. What's nice about having it set up that way is I can go back through and say, well, what if I was doing this at 375 degrees Kelvin? And you get the outcome where you can see, in this case, it's really tight around this region right here. So this 10,000 is probably too big of an energy step. Maybe I'm only going to stick to 5,000. And you can kind of quickly see based on your numbers, all right, so we cross over to sort of useful range really sits in this point right here. So the top and bottom range is really only about 16,000, 160,000 kcals is the absolute bottom end. And then we start to cross over to useful down here at about 80,000 or so. So all I'm emphasizing is Excel is a ridiculously powerful tool for these kind of what-if hypothesis parts. You know, not only, yes, you can do the direct math and do the individual solutions. The downside, the thing I don't like about that is you have to really know why you're doing it. Like if you knew I'm trying to find two values, maximum, minimum, it's a good thing to do. What's nice about using a tool like this where you can sort of set up with these ranges and do these kind of visual assessments, you can browse your data a lot more easily. And you can do the same thing where like some of the other things we've shown in the other lectures, what if my data had more or less error? You can actually set up a data series like this with like a random number or something to represent your error and show, well, if my error was this big, here is what my fit would look like. If my error was much smaller, here's what that would look like as well too. This is just something that, when I first learned about just, okay, basically coming up with synthetic data by these kind of running sequences gives you a way to sort of more quickly manipulate or come up with a tool like this to kind of do these kind of scanning behaviors. Using something like this is that first half where I'm saying, all right, based on this component, I can kind of model what's going on just this side of the equation. What I'm going to assign for you guys to play with is the same thing where I want you to build an Excel sheet like this that solves for that energy difference here to give you a selectivity constant, right? So this is where if you imagine you have two competing rates, how big or small does that energy difference have to be to give you a pathway or a concentration difference between the two? All right. So in the example that we went through with the dynamic resolution, this is just a first case where what we have is an equilibrium in the middle of two selectivity determining steps, where because it's an enantiomeric, this is all on the same energy relative to each other. But what this matters in terms of like how we choose which side or the other, when we have multi-transition states, I just want to drill back to a second to the question, I think one of the things we did very early in the class was this question around what does this delta G naught actually mean in terms of selectivity, or especially what is the rate limiting step for different cases. Now for simple kinetic steps, we're looking at that single barrier over here. If we go to multi-step like this is a case where if this was your reactant in each one of these cases, remember based on what we said before, where would you put your turnover limiting or rate determining step in each of these cases? So case one over here, you've got transition state 1, transition state 2. What is actually sort of driving the bus in this sort of case if you had to sort of assess this energy diagram? Yeah, number 2 is probably going to be the one that's going to be your turnover limiting step, which means you've got an equilibrium between these two, and it's going over this barrier that matters. In this case 2, which is it? So again, reactants. First step is probably going to be your slow one, because after that, your equilibrium lies after that. What about this one? First or second? Still probably going to be your second, right? Again, you'd have to get on there with a line, but this is still a little bit higher between the two. What's happening in these cases, and again, if you want to do this decomposition, really, and this goes back to that first article we talked about, what was this highest jump versus, or biggest jump versus highest barrier. Really what it comes down to is doing small decompositions of just this kind of simple system. What we're looking at here is very similar to how we did the derivation of the Eyring equation. If you have two steps, you can actually break this down and say, look, if I was looking at this, like the derivations we did before, since this is my biggest jump, or my jump I have to go through in this step, The actual rate of product formation is just your intermediate times the K, which comes from that barrier height. That's the derivation we've said, where that second step in a multi-step sequence is going to equal the rate of product formation. So this goes back to the steady state approximation we did in the first couple weeks. Okay, well, based on this, if that K comes from this barrier height and the intermediate concentration is really the material just before your product forming step, we don't know the intermediate concentration, but if this is an equilibrium, these two guys are equilibrating with each other, I can actually come up with an equation for I, which is just intermediate over reactant. Products over reactants is the capital K value, the equilibrium constant, for that very first step. Okay, so I can rearrange this and I can solve for I, which means the term I can be expressed as the capital K value times your reactant. So it's just your reactant and the capital K as a result of the equilibrium there. Remember, that's your forward and backward rate constant, or your products over reactants of those two. So this is the same thing as like the steady state approximation. We usually call this what we call pre-equilibrium. We're saying I can approximate the intermediate concentration by assuming reactant and intermediate are in equilibrium with each other, which means capital K for that step is just intermediate over reactant, and I can solve algebraically for that I term in this way. When you're set up like this, now what you can see is you've got an equilibrium constant and you have a rate constant. So rate constants are given by the Eyring equation, which is your delta G double dagger. Equilibrium constants are given by your normal minus RT ln KEQ. So the KEQ value is given by your normal equilibrium, and then all that's multiplied by your R. So what we've done is we've expanded those two K values into two terms that are now exposing the delta G, the delta G here, and the delta G double dagger over here, and we're putting them in terms of just simple constants like RT and your Boltzmann distribution, your temperature. If we rearrange that, we can, because we're over this constant RT that can be aggregated together. Now what we have is just a term here, which is just your delta G. It's the sum of those two. This is really just Hess's law, right? What we're saying is, if I am trying to figure out the barrier height to go from reactant to the transition state that is actually running this whole show over here, I can get there by the sum of the barrier from reactant to intermediate, my delta G naught value, and from intermediate up to that transition state. So that mathematically, this expression here is just saying that the overall delta G double dagger is just that plus that. That gives us our overall component. And again, that's just Hess's law. If I have an energy level diagram and I have more than one way to reach to a single point, I can take two energetic features, both the delta G and the delta G double dagger, sum them together, and I now have an expression that gets me all the way to this point over here. So we're just saying this is what the same expression is going through. The overall rate, or the K value, or K obs, is just going to be your reactant constant multiplied by that overall barrier, which is just the sum of the two individual components. So you can decompose them. So, and that's universally true. Doesn't matter how complicated your system is, going from some component where you're like jumping over to this highest barrier is just this Hess's law permutation. The rate determining step, a transition state, will always be the highest barrier from this particular component, and more importantly, the observed delta G double dagger of that step is just that equilibrium constant and then that rate constant, those two species. The only time that this gets weird is when you have so this is just for all three of these ones. The observed rate constant delta G double dagger there, which is just that one plus this one. This one is just that first step. This one is really just that second step, which is again, you can think of it as that equilibrium constant followed by that rate constant, the small one after it. This is the only case where this breaks down. If you had a reactant that goes way downhill in energy to an intermediate that then has to climb out of that hill, this is that case where it looks like highest jump, right? So if you looked here, the highest barrier, yes, it's still that second step, but the reactant has to jump down into a hole, and then it's got a very large delta G double dagger in order to continue forward to your products. This is a case where when we've had those arguments where people are talking highest barrier versus highest jump, this is the case that people point to as like, oh, no, the highest jump one, not the highest barrier. Because it's possible that maybe the surface, if this barrier was just down a little bit, that would still be your transition state that's returning over for that would be controlling the rate of your overall step. Why this breaks down is, This generality is absolutely true as long as your starting material and your product are the two lowest energy system. If your intermediate is lower in energy on your energy surface, like this, you have to treat this as two individual steps. What this is, and if you had a diagram that looks like this, really this should be thought of as the reactant turns into the intermediate. That's one reaction, and you're done. Now its intermediate goes to product. That's a second whole step that you treat independently. And really, all that we're saying is if I have to fall into this really, really deep hole, the better way to think about this is actually, I have this intermediate here, and it's making a decision. Do I go this way, or do I go this way? Right? Think of it where this is almost like starting the chemistry at this intermediate. It's like that book fold where you're going back to reactants or over to product. Because when you start, again, if you imagine measuring this, this is a case where you might throw in your reactant. All of it's going to convert to the intermediate, which is now in equilibrium with your starting material, and now your product is coming out of that point. So it's more like thinking of it like what we've been talking about, where you're starting the chemistry effectively here, and it's now a selectivity left and right, rather than two individual steps. So those are your basic points. But this is what gets to what's called the Curtin-Hammett principle. This possibility of saying I have both equilibrium, so delta G, and I have rate equations, delta G double dagger, that's going to tell me both my product distribution, overall rate in a system. Now, if I gave you just this picture and said, you have an equilibration between A1 and A2, and you have two possible products, B1 and B2. I now know I can measure the equilibrium constant, A1 to A2, and that's just products over reactants. I could do A2 over A1 at some time, and I could tell you what the capital K value is for that particular equilibrium. And in this one, we're saying A2 is more stable than A1. Based on just this information, which of the two products, B2 or B1, do you think wins?
I feel like you wouldn't know because it also depends on how fast that equilibrium is compared to the K1, K2.
That's part of it. So maybe the overall speed might be, so give me a scenario where that might be your problem. So you're saying that A1 to A2 has to, if it's very slow relative to what? So in your one, the way, maybe let me sketch it. You're saying if this equilibrium was really big, and let's say this was super tiny, and then this was super tiny sort of thing. So basically this barrier is large for this interconversion. So really those two, in that case, you're right. This one right here, if that's the largest barrier, that's kind of the wall between those two, then really the product distribution is really down to just these two guys, right? The A1, A2 population is going to reflect your B1, or your B1, B2 population because interconversion is slow relative to. That's true. That's absolutely right. Give me another scenario.
If A1 and A2 are very similar in energy, A2 is favored a little bit, then let's say K2 is super high barrier and K1 is low barrier, you're going to be B1 would be favored.
So you got that versus, let's say that. So in this case, sure, what you've got is rapid equilibrium here. You got a wall, and that's the way you have to escape, right? This is the Curtin-Hammett scenario. Really, all the Curtin-Hammett, so if we kind of go through and build up this curve, what we're saying is the delta G between those two intermediates, really what that is that's defining your KEQ. If I've got this KEQ, I can define it numerically by the concentration of those two species, products over reactants. Because of that, and back to this, your primary thermodynamic equation, you can look at KEQ is equal to RT ln KEQ. So we can put this in terms of its energy height. So we can both go back and forth between the size of the equilibrium constant, and then at some temperature, we can get a size of what that free energy actually is. Now, product distribution, the rate moving to B2 versus B1, that's just the rate of B2 over the rate of B1, how fast the two guys form. We can re-express that in terms of their activation energies. So the rate, this one here, is just K2 times A2. So it's your concentration times your rate constant. And then going the other way, K1 and K1A1, which is going over to your B1 compound. That's the concentration distribution between the two possible rate constants, right? So that's just going left and right depending on what those barrier heights are. And because we set it up that way, This concentration ratio here, we know that's actually equal to KEQ. So first thing is, really the relative rate going to product 1 or product 2, you can express it just in terms of an equilibrium constant and 2 rate constants. It's the rate of formation of your 2 products, so K1 with K2, and the equilibrium constant between how much A1 and A2 you actually have. So the concentration disappears. Like it gets still baked into this value here, but now what we're dealing with is just constants in a system, which comes back to just their delta G's. So since I can re-express these K's back as their delta G's, I can expand that, and all I'm doing is saying, look, K2 here, that's the Eyring equation for K2, where you just have this delta G2 value. I've got my Eyring equation for K1. That's just, again, now you've got this delta G double dagger equation for K1, but everything else is the same. And then finally, that is your thermodynamic equation of your capital K. That's your delta G of those 2 systems. Now, because the signs are positive and negative, we can actually go through, and now we've got a whole bunch of common terms. All of that junk compresses into that, right? So we can actually squish everything together because we have a KTH on the top and bottom. Those are common. That disappears. So boom, all that cancels out. Now what we have is a bunch of common E over RT equations. So we just make that common over here. And then everything else comes neatly together as a package as just a sum of 2 different transition state delta G's and a delta G, or 2 different delta G double daggers and a delta G for your overall rate constant. So what that just means is we can rewrite this where this energy difference here is really just, again, Hess's law. We're saying that it's just the sum and difference of the different values that's baked into our system. Because we've got a negative delta G in this particular case, that's why we're getting sort of that delta G 2,1, or that the way we're expressing it there, it comes up with a different sign. But really what we're trying to say is the product distribution that you get here really is only governed by the rate, the barrier height between those 2. The delta G between your 2 determining steps is the only thing that determines how fast this rate goes. It has nothing to do with the equilibrium anymore. So which compound or which product, A or B, forms faster is always a transition state argument, no matter what you see. So going back to what you mentioned first, Morgan, this example here where maybe I've got something where this is smaller and this is smaller, it's still that same point where the highest barrier between these 2 just happens to be the one in the middle. So this is the general solution to any of these kinds of problems where that delta G is the fundamental thing that tells you what the rate of formation of those 2 are, and also the product distribution. Why this matters is that is your more stable state. So even if you had something that you could start in the middle, this might be the thing where all your molecules sitting, but to go to product this way is so much slower than this way. So as a result of that, even though I have to go to a higher energy material, I still have a way out of this manifold by this pathway. So effectively what you're seeing is a more stable material going through a slower step still loses overall compared to a less stable exit that goes through a faster component. So the population of which intermediate you have might determine what you observe in the pre-equilibrium, but the decision of how your reaction sort of escapes to your product is still only governed by this. It doesn't matter how convoluted this kind of valley is, it's those 2 peaks that are just going to determine it at that point too. There was an analogy we used to use of blindfold a whole bunch of students and set them loose at the top of the gondola and see where they come out. Eventually it's your peak height, and it's between those 2, wherever you fall off there. So I think the chief still wins if you actually go by the geography. So it just means that no matter what happens or how complex the system is, you can reduce it down to this core center and say, I have a pre-equilibrium, and that's the part you might actually observe in a catalytic system. You may see multiple species equilibrating between each other. But then whatever barrier is your first irreversible step, it's the delta G between those 2 transition states what's going to determine that distribution. So in this case, your 2 product distribution is really going to come down to something that's being dictated only by this part. Now, for the principle to hold, you have to have these 3 key assumptions. You're assuming selectivity. Basically, once it's made a choice, you're never coming back. That's the most important one. So there's an irreversible step that after it's made that choice, you are fated to one single product. Second is the equilibrium down in the hills, it must be rapid. That goes back to that point where if the equilibrium is slow, then no, you're drawing one product away from something else because they're not actually in communication with each other. And the selectivity has to be constant over the entire reaction. It can't be changing. If the selectivity is changing, then you're changing your mechanism. You may be introducing a product which is acting as a ligand, which is giving you a new transition state or something like that too. But as long as those three things hold, you will, this kind of overall mechanism works. And again, the thing I love most about it is it doesn't matter how ugly the math is. This is just Hess's law and a simple linear sum of delta G's. And again, once you can express it as delta G's, you can reduce those back to K's based on a certain temperature. You can actually estimate in advance what you think your selectivity would be by doing a couple of measurements at a couple temperatures and estimate what that barrier height is. You should be able to predict what temperature you should move this to in order to achieve some kind of an outcome based on whatever that energy difference actually is. So solving for temperature to achieve a certain ratio is easily possible once you have this too. And again, I like using this in a sense kind of like what we did with the linear free energy thing. If you're trying to fight on a problem and you're like, at 10 degrees, here was my selectivity. At 40 degrees, here was my selectivity. You can do this math and say, if I cool it down to liquid helium, I might get the EE I'm looking for. And then now it's a decision of do you want to try and do that? That's where solvent effects have to come into it again too. So there's a couple quick examples where you can see these kind of parts. Classically, this is one big one. If you had, let's say, pyramidalization, inversion around a nitrogen, and if we had a molecule like this where we're kind of conformationally locked, the T-butyl group is going to be in an equatorial face. You can look at this where the lone pair and the nitrogen is being rapidly equilibrated between sort of the equatorial and axial plane. Now, obviously, the methyl group out here in the equatorial plane is going to be way more stable. There's no A strain around that. And it turns out that that molecule, which happens to the more stable equilibrium, also produces your major product. And really, this is something that this is not the sort of classic Curtin-Hammett where the more stable material is not predicting the major product. This is where everything is in the same direction. All we're saying is the energy level diagram for this might be my starting material 1, which is, like, let's say starting material 1, and starting material 2. I could sketch out a diagram between these two that says, all right, starting material 2 is going to be more stable, starting material 1 is going to be less stable. I'm going to connect those by a rapid equilibrium. And it just happens that that transition and this transition are probably similar in overall barrier. Alkylation here, right? This size here, delta G2, and this size here, delta G1, are probably almost equal to each other. The difference here is since you're starting from a high energy state of that starting material 1, that just bumps the entire barrier back up. So the absolute barrier going, basically alkylating where the lone pair is in the equatorial or axial plane, there really is no difference in energy between those two, but because you have to start on a higher energy surface, the overall delta G, this value right here ends up being bumped up based on whatever that energy difference is here too. You're just basically elevating the whole point. So it doesn't have to have any other selectivity rather than coming from a higher energy component, but you end up with this starting material 2 being more selected as a result of that. The other option is where you have the reciprocal, where some reason there's a difference in energy between two different phases. So this is the same pyramidalization, but the difference now is, so you still have rapid inconversion. The more stable material puts the methyl group on this phase where, again, you're away from the steric bulk on that particular point. However, alkylation over here, the same thing that makes this more stable in that case by having the bulk away from the bulk, what that does is it creates a slower step for that alkylation. It's harder to alkylate on that face now. So now what you've got is a little bit different sort of an energy diagram. So again, if you sketch it out, let's say this is S1, this is our S2. We could try to sketch this out where we've got S2 is lower in energy, S1 is higher in energy. We've got a connection between the two that's still rapid, but now going to product is going to be a bigger jump over here and a smaller jump over there, which gives you some delta G here favoring your S1 product. So this is a case where the observed intermediate, the more stable intermediate here, does not predict your major product. Your escape goes through the higher energy component too. And again, so what you'll see always different permutations of these two phenomena. Really what you're saying is that it's like a Hammond postulate. The transition states are similar to each other because of structures of the transition states are similar, therefore their energies are similar. That's an example of this. Here's a case where the two transition states for these SN1s are probably really similar to each other, so that second step, the delta G or the delta G double dagger, green versus red, is probably about the same size, versus this one. These two delta G double daggers are going to be very different because the environment between the two of them are going to be very different. And as a result of that, you're getting this push and pull behavior between the two. So that's where I wanted to cut off for today, but just anything else. If you guys experienced this before too, if you've run into systems where you've seen this kind of behavior where stable intermediate does not predict geometry in that point too. Especially in catalysis, it's super, super, super common. Okay, I will see you guys on Friday.